Hi, this is Coffee Compiler Club, and anything to do with compilers and language runtimes and garbage collections and typing systems is all fair game. You're being recorded live. You'll show up on YouTube within a couple hours, typically. I guess a little longer now. My upload's not as good. And that's the end of my spiel. So that's it. I don't have much on the AA update. I've been hacking theory bits in between moving in. I'm still settling in. It's getting better. I have non-compiler things. Turns out when you live in the redneck part of the world, it's a half a mile, 4/10 of a mile to where the garbage truck comes to pick up my garbage. So not interested in hauling my garbage cans 4/10 of a mile. You can buy a thing that you attach to the back of your car, lets you tow your cans on their own little tires 4/10 of a mile, and it daisy chains behind like a luggage carts out of an airport. And like half the neighbors have it, and it's just a common thing on the road here. There's like 20 of us on this little private road, and Thursday afternoon, cars going with a train of cans behind them. It's funnier than hell.
Just riding with my cans.
It's yeah, exactly. It's like, what the frick? I'd never heard of such a thing. You go online, you go look for, garbage can car haulers, and suddenly there's a website. It's a thing. People make these things. Like,
so
who the hell
garbage cans there is no better way to start with garbage collection. So
there you go.
Smooth jump in.
Fine. Ask a garbage collection question.
High latency of like 2 weeks or something.
Exactly.
not nice for high frequency trading, I guess.
Yeah. First time I hauled the cans up there, it was kind of fun. Say hi to the neighbors, Second time's like, no. Get this done. All right.
So does somebody has a topic?
Yeah, right here. I'm pulling in camera, and then we'll poke at something here. Mostly, yeah. No AA news. That was the hard part there.
But, on the topic of garbage collection, I had a general question in my mind for a longer time. So, what do you all think? What's currently the best compromise of a garbage collector in terms of ease of implementation and general performance?
Oh.
So I think you have the three basic ones: the mark and sweep, mark and compact, and how's it called?
So I believe there are generally two categories. The less precise the garbage collector, the easiest to implement. The more the knowledge it has about your program, it's harder to implement, but it's generally faster.
Yeah, I would require that all the stack is precisely known. And
so
go ahead.
The real trick here is that all your bugs come from the core implementation of the connections to the runtime. And then so you start with the easiest possible collector that you can envision to get the bugs out of everything else. And the bugs will be, you didn't mark your stack right, you didn't crawl your stack right, you weren't concurrent enough, or you were too concurrent, threads were running while you were mutating, you didn't implement your read barriers or your write barriers or your card marks correctly. Any number of 1,000 things will be wrong that are almost unrelated to which actual collector you're using. So you go to the simplest possible collector, so that's not the bug. And then you build up an infrastructure of tooling to help you debug garbage collection bugs. So shit like run my program as deterministically as possible, and then do whole heap sweeps for wrong, missing, bad, broken bits that are really slow, but do them with like exponential drop off with numbers that I can do binary search for at what point did I drop the bit and break myself. That's the
right.
Once all that's going, you can imagine coming around to, sorry, I'm picking up Dan here. It was
The third one was semi-space. That's
Yeah, sure. Yeah, like I said,
so would you even bother with using one of them for the easiest kind of implementation,
yeah,
or would
you
you?
mark sweep is probably your easiest one. As soon as you, and that will crash when you have leaked things incorrectly. So a nice debugging property is to scribble over all memory that should have been collected, so your other folks die quicker. And then anyone who moves will have another round of bugs related to you held on to a pointer that didn't get updated, but all the objects that it pointed to got picked on by somebody else, so that you didn't notice that you weren't following this pointer. And then as long as you're moving things, so the first step is a non-moving collector, and you just find all the root places and you miss them. And like I said, and then you get some debugging tools in place to help you find all those. Then a moving collector will find all the guys that got pointed out by somebody else. You didn't notice you didn't have them until they moved and didn't update. You gotta get those bugs out. And then if you go to a generation, you typically have card marks, and you'll find all your card mark bugs. If you go to a concurrent collector, there's typically phases where you have to start and stop threads. And you'll have to figure out that you have or have not correctly started or stopped all threads. The easiest one is obviously a stop the world collector. And of course, Hotspot had, quite a while of finding the bugs where the stop the world collector failed to stop all the threads that it should have, because there were threads you didn't need to stop because they didn't talk to the heap, except that they did. And then you get really concurrent, where you go through phase shifts, and then you have to know that every thread has passed before, after, and you have to get the whole ragged checkpoint thing sorted out, where everyone has crossed some threshold, and then you begin mutating pointers or not, or whatever. If you do a read barrier, you have another set of bugs. So these things all add bugs, and you kind of want to have stable before you go to the next one. And so it's all, it's all about the runtime connection. The actual algorithm for the garbage collector is like I said, it's like almost, it won't matter for a long time. That's not where your bugs will be.
So a good approach would be the staircase. Start with the simplest case, non-moving, just mark phase and sweep phase.
Yeah.
Then try it.
You'll have plenty of issues there. And like I said, you end up with an infrastructure that you build up to help you diagnose and debug garbage collection bugs.
So each step is kind of lower step to the hill or something like
that. Yeah. And they don't all have to come in a particular order, and you can skip some if you want to implement a single collector and it's a particular one, you don't need necessarily the other parts or whatever.
They then become trickier and trickier and trickier.
Yeah. You talk to the GC researchers, and they say you want to have a runtime with a really solid ABI that you can code to. And the hard part for that one is that, no one came up with a really nice definition for that ABI without it being brutally ugly to implement. And many GCs didn't care for many of the hard things to implement that you needed, right? But there were some cool GCs that did, but they didn't these other things or whatever. And so there's these, garbage collecting toolkit theories, and they all have difficult issues with implementation. Unless you subset the kind of GCs you're going to have. But they can point you in the right direction. Hey, I need to have the following things. Well, you need to stop a thread, crawl its stack while stopped. Oh, by the way, if you ask the OS for the stack pointer of that thread over there that you just stopped, he will lie to you with low frequency. 100% chance he lies with extremely low frequency. So you cannot rely on the OS's call to give me that guy's stack pointer and his program counter, because it will be incorrect with low frequency.
So so that the collector after your easiest one, would you basically focus on the concurrent, or like making your easy one concurrent, or would you rather have a look at?
I would do the Zol concurrent collector in a heartbeat again. I understand how it works. The results Zol got out of it were really good. If you're going to go concurrent at all, if you're not going to go concurrent, like H2O big data calculator didn't really need a concurrent collector.
The Zoo pauseless garbage collector?
Yeah, the Zol pauseless garbage collector. Yeah. Yeah, we got super good pause time numbers out of it, like ludicrously good numbers that Oracle a decade later still can't touch. That is the
There was
collector of choice for high frequency traders.
some 50 microseconds or something.
Yeah,
like
it's
that.
something ludicrous like that. Yeah,
Yeah.
it's hard enough. It's good enough to run hard real-time things reliably with a garbage collector.
So, regarding the ABI point you made, I'm always wondering, new architectures have usually plenty of registers available. And it seems that usually the runtime or the garbage collector or whatever you call it don't really make that much use of the newly available register space. And
For the case of Java, it starts as a stack machine, but pretty quickly it converges to.
Yeah, as soon as the JIT gets involved, that's a lie.
No. All right, yeah. I was wondering which I'm thinking would the runtimes we have today use the available registers for more of the bookkeeping if we hadn't had like x86 with like very little registers earlier on?
No, back up. I run JITs from 8 register machines to 64. 32 is clearly the sweet spot. A JIT can make good use of 32 registers. 64 and 128, rarely, you do have more issues actually using them well. So unless you've got 64 registers or more than 32, I claim the JIT will happily use them.
All right.
So
And
yeah, and you're going to burn one. You're going to burn one for like a stack pointer usually anyhow. You may burn a second one for something. Some people do, some people don't.
Doesn't assuming more things about the garbage collector doesn't somehow dictate a calling convention or ABI that has
There are some things to be aware of in the calling convention for garbage collector. Yes, there are not very many. You can get excited about the garbage collecting interaction with the ABI, but the only thing I found that made any difference was callee save registers. If the called function has caller save registers, he doesn't know whether they contain pointers or not. He just is supposed callee save registers. He has to save them if he's going to trash them, but he himself does not know if they are pointers or not. So when he saves them and he marks them in an OOP map, so here also supporting your bugs, by the way, is your OOP maps are incorrect. He has to flag it as, I don't know if it's a pointer. You have to go ask the parent frame. So then the stack crawl code has to crawl through this frame, see a spill space on the stack, look up the OOP map. It says, I don't know. So he has to remember it and crawl again. And this can happen recursively. Also, there's no reason the JIT saves things in exactly one place every time. It's a hard thing to make a register allocator guaranteed not to do. So sometimes that one value may be spilled in several places, and now you have a tree of possible values that could belong here. And so it's easier to not have callee save oops. You either have an OOP in that register, then it's not being passed, it's just going to be empty or contains an OOP, or you just declare there aren't any callee saves and the caller just saves and restores as he sees fit. So there is some calling convention shenanigans you want to talk about with the JIT. And this is by the way, this is all matters like JIT calling JIT, nothing to do with interpreted and nothing to do with stage 0 JIT. Your high quality JIT calling your high quality JIT with the lowest possible overhead at that call site, the highest performance. What are the rules you want to put on it? What does GC add to a rule? Well, you're going to have an OOP map at that call point anyhow. Now, do you want to have any other rules? Well, one of the rules is your OOP map is complicated, your stack call is complicated. That means go straight to your pause times for a low latency collector. For a high latency stop reward collector, it doesn't matter. The pause time for one thread is drowned in the full GC cycle. But if you're doing a low latency, pauseless, low pause collector, stack call times matter because you can't obviously run while your stack's getting crawled. And if your stack crawl is complicated, that impacts. So now decide how you're going to make it less complicated. Another option is to, well, I guess I mentioned that one. You can save some call, he saves as declaring as oops, and some call he saves as not oops. When you make a call and the caller has to, at the call site line, shuffle the non-oops out of the oop registers and vice versa, so that when the stack call happens, you can just say, it's an oop, and I don't care where it came from or what it is, it's an oop, and therefore I'll crawl it. It might be dead from the caller's point of view, it might be dead from, I don't care, I'm gonna crawl it, it's an oop. And he's stupid and quick. That's sort of the main goal out of that one. And then, you know, that's probably the main calling convention shenanigans. There are other things that you think about, like you want to have a thread crawl his own stack, but that gets to low latency because it's all hot in his caches. So stack reads and writes want to be done by the thread who's actually running. Pause threads, you also want them to pause at a safe point so their stacks can be crawled. Because like I said before, the OS will lie to you on rare occasion about where things are. So you can't ask the OS where that thread is. So you want the thread to tell you himself where he's at, which he can do right before he goes to sleep at a safe point by putting a PC and a stack pointer in a known location. So that's how we did it as well. Just throw it in a thread level storage. This is the start of my stack. I'm now entering native code. I'm probably going to block for IO. Call my stack starting from here going up. That gave you a reliable way to crawl that guy's stack because he's asleep. You can crawl it in the background concurrently. No one cares. It's all fast and easy. If he's not at a safe point, you can't crawl a stack till you wake him up, roll him forward, sleep him again. Given the cost of wake up, roll forward, and sleep is actually significant, but you don't want to go there. So then you want to have this cooperative safe point thing and shit. So there's a whole lot of shit about low latency collectors to add a lot of overhead to the discussion.
An interesting point would be, does it have some array of research that so we basically your program based on a location pattern defines a regions where there's in this region is only bump allocation in order to minimize, so the garbage collection always can have all of your stack. And so instead they're based some regions that it's reserved to only bump allocations because it knows based on the usage pattern of the program it can safely deallocate it.
The only regions that I'm aware of people living with were, you know, long lifetime things, so old gen, big objects, which you don't want to move ever. Little objects you're going to move and compact after they run through, you know, enough generations of young gen cycles, and you declare them old or whatever.
So the generational side of things is some like that. All the objects die young, so just bump it. Okay, the long lifetime objects are in, you know, all the separate regions.
Right. You're asking for. There's other people who did things like pointers with this particular shape are known to be of this kind of a class of thing. So I don't have to carry the GC bits in the pointer. So
I don't think it's too much. It's a GC because you can emulate this behavior with an arena, basically throw away and start again.
Right, and then there's bump pointer for which the GCs all do things separately. Like those are thread local allocation, so that one thread doesn't have to do an asynchronous atomic update. And he just goes to the main GC and says, carve me another TLAB out of the heap. And he, you know, the GC hands you a TLAB. In there are other games you want to play, like carve out chunks the size of a TLB entry so that each running thread doesn't burn yet another TLB entry besides the one for their young gen heap allocations. So that immediately means TLABs on an x86 are of size 2 megabytes. They're either 4K or 2 megs, and 4K is getting kind of small. So 2 megs is a good size. A bunch of, and align 2 megs, but a bunch of shit like that comes around. You want to start thinking about when you add in, when you think performance and a garbage collector is sort of separate, but what are the performance issues to know ahead of time? If you're implementing one from scratch, that's what I hear Simon saying. Don't do all these things yet. Leave yourself open, but know that they're coming. and find all your first set of round of bugs, which is like, I stopped the threads, I got their stack pointers, I crawled their stacks, I found their roots. I then ran my mark sweep, which just followed all the roots and did the right thing. And then it took everything left over and threw it on a free list. Now I don't have a TLab, I have a free list to allocate from. Okay, fine. And then I have a hook that says I want to allocate. I go try some bump pointer on a narrow thing and it ran out and it went back to the GC, which did a free list thing behind my back and hand me something, whatever. You have to work out that interaction because you'll hit it plenty. You know, the TLab ran out, now what do I do? And then after you get a compactor in, you get a sort of a proper TLab, and the callback for more memory becomes much less often. And that's a performance, really it's a performance hack.
This is kind of contention point at GC, because the JIT collector can work to figure out what can the escape allocation, because it can figure out, it can just not allocate the object, just stack allocate it. There are just a lot of things interthread with the GC.
Yeah, escape analysis is sort of unrelated. Is that what I heard you say? Like,
I believe it is, because if you figure out to not allocate object at all, just to allocate it the stack.
Yeah.
So
right. What does matter is that the compiler, the JIT, and the garbage collector handshake via OOP maps. So you have to make sure the OOP map generation is correct. And that's OOP is object oriented. It's a managed pointer map, right? So that there are a bunch of rules there for the JIT. So if you start with an interpreter, it's not a problem. The interpreter does this at has a fixed stack frame. It does it at every bytecode or wherever you're gonna do it at. You do it from a JIT, then the JIT needs to have a rule like there's always one of these in any infinitely long piece of executing code, which means any loop that you can't bound has to have one, because otherwise that thread runs forever and never hits a safe point. You have to have a way to declare that this thread stops, so that thread can trigger a GC. So the running thread at a safe point has to have a mechanism whereby he understands it's time for him to stop. So Azul, we went to polling, which can be made, you know, half a clock cycle on an x86. You thread level storage, test a bit that's hot in your L1 cache and is correctly predicted as you're not stopping. So that's a half a clock cycle, but you had to think about it. In the land of Sun, the original, early Sun, not Oracle, the original stopping mechanism was you patched code with a breakpoint and the thread ran over it and took a breakpoint. This turned out to be highly problematic on a lot of fronts. I highly don't recommend it. If you want to go down the path, I'll tell you the long series of fail modes that come with that. Non-obvious fail modes.
Please do, I would be interested.
Do you actually want to hear them? It's like shit.
Yes.
Sure. So you can't patch all the JITted code. There's way too much of it. So you want to patch just where people are running. So you stop all the threads once, ask them where they're running approximately, get their method, patch them all, and start them up again. Okay, they all come to a safe point after a while, or maybe they escaped the running thread without hitting a breakpoint because the x86 has no guarantees on when you edit code and when it hits the running processor's pipeline.
So this patching happens while the threads are running, or are they some kind of?
It was attempted to do while the threads were running also because you wanted to have like fewer stops. So how slow do you want to go? So the first cut was ask the OS where the program counters were, map those to code locations, map that to OOP maps within that JITted code, patch all those locations. So those locations were all arranged such that they had a start of an instruction at an OOP map point, and you had it all, and that's fine. And you threw down the one byte patch instruction on x86.
And
so,
after you were successful, you also had to revert all the patched places.
Oh yeah, totally, yes.
Okay.
So now some count of your threads stopped, some count of your threads escaped the method they were in without hitting a breakpoint because the timing was wrong. So you look at the set of running threads and you stop them again, and now you ask the question again, and of course the OS periodically lies, but you think you know where they're at. You throw down breakpoints in new sets of methods, and then you wake them up and they run again. And the running stops most of them most of the time, and occasionally another one gets away, and you stop it again, and you patch and you let it run, and you keep lather, rinse, repeat till the last man stops. and you finally have them all stopped. And then you can go unpatch all that code that you patched.
So if you're unlucky, you have one thread that prolongs the time to stop for
everybody.
all others.
Yeah, right. When the OS lies to you, if your code was not robust against the lie, which we didn't understand that it was going to lie, you would just crash when you got a stack pointer back that was junk, and then you would do a lookup, and the lookup would fail in some weird way, and you got a bad answer. So it took us a while to discover that unrepeatable, non-reliably, low frequency, we got a lie back. So you had to start filtering the stack pointers in the first place. So you had to make sure they were sensible before you could begin in program counters, both of those, however you did it. Because you on the x86, you took a stack pointer, what you got, and you reversed that to the program counter using the return PC address.
So were these lies documented? Was this errata for certain CPUs, or was
no? So as of I've mentioned this before at talks at large public conferences, and then I polled the audience 15 years ago and said, I think this is true. Does anyone want to say that's, that's a lie? It's always reliable. And no one said anything. I said, does anyone think it is unreliable? I had several people raise their hands, and I asked several variations of Linux. People admitted that they weren't sure that that path was going to be safe. So you can imagine scenarios where you're running along and you take a TLB hit, and you go to the TLB handler, which triggers a Stack Overflow, and you go to the Stack Overflow handler, which hits a page fault, which goes to some sort of out of memory swapping code, and then some other thread, which is all fine, asks for your stack pointer. And what the hell did you get back, right? Did you get the page fault handler? You get the Stack Point Overflow handler? Did you get this handler? What the hell did you get back, right? So it's like garbage. Sometimes you just got uninitialized memory back, was another common scenario. That he hadn't bothered to fill in the backing memory store to get the return PC, which was stored on the stack, because the TLB fault handled and happened, and he hadn't actually, he stack puked in the interrupt handler. The PC was buried in the stack puke, which is definitely processor specific. And until the interrupt handler returned from the interrupt, he wasn't going to then rewrite the PC on the normal location on the stack. But he fed you the normal location on the stack, so you got random uninitialized memory for your PC, and shit like that was going on, right? So this was the common case. I asked again as recently as like 5 years ago, and got the same answer from people who admitted that they just weren't sure that in fact it would be reliable. So at this point, I already worked out the Azul collector and had it observed it be unreliable on Solaris and on 4 or 5 revs of Linux and on something else. There were several other ones that we observed rarely, that things we didn't know what to do with, that we blamed on this. We were pretty damn certain was broken on Solaris, pretty damn certain was broken on several revs of Linux, probably broken on several others, probably broken on Itaniums, probably broken on some variation of OS2, and I don't know about Windows. Fine, okay.
And it sounds like the failure cases happen more often under high load, so it's probably also hard to reproduce.
Right, these are all non-reproducible, and again, all your concurrency bugs happen under high load in non-reproducible ways. So these are the worst possible bugs to go try to track down and figure out what's going on. So the easy, straightforward answer was rely on shared memory and the hardware's processor memory management rules, which were reliable enough. And that one was, when I'm about to go to a place where I can't stop, but my stack can be crawled because I'm going to block for IO, for instance, or I don't know if I'm going to block for IO, whatever. When you go native code, anything like that, you record your stack pointer into your PC. If you want to pull a thread to tell them to stop, or you want to find out, do a GC, save point, whatever on one thread, we flipped a bit, and he's running normally. He free runs, and if he runs into testing the bit, he'll save a stack pointer and then tell you he's done and he's out of there. If he's already out of there, he's already saved that stack pointer and he's already told you he's done. And what this means then is that to allow progress, you have to treat stacks as a lockable resource. When a thread is running on it, he has his own stack lock, and he is running on his own stack and changing it furiously fast. You cannot see how fast it changes, it's just a blur, obviously. When he wants to let go, he releases that lock. If the garbage collector takes the lock, he has to ask the running thread, are you out? Because if you're not out, I can't take the lock because you're busy mutating. Then at the lock handoff, the garbage collector has it. He can now force the hardware to flush things like register windows on a bunch of register window hardware we did. Itanium, Azul, Sun all had hardware register windows. You flush the hardware register windows, you force coherency. You now can look at the stack. You can now edit the stack. When the thread whose stack.lock wants to start running, he has to take his lock back. He has to do a lock acquire. If that fails, he blocks for GC.
Is that locking on a high level, or does it use a locking instruction, for example, where it can?
All locks have to be on some sort of atomic abstraction at the bottom. So somewhere at the bottom, there's a X locked, X whatever.
But synchronize it is a lock for a block, but the hardware instruction, whatever it may be, is just on a much more lower level.
You have to use a hardware instruction right at the bottom. Now, the lock wasn't exposed to the Java user like a Java lock in any way. It was conceptually a lock from a non-Java mentality point of view, right? If you threw Java away and just went back to pre-whatever world, of course, people did locks all the time. You're a C person, you do multi-thread, you do locks all the time. It's fine. So you have a lock-like thing. You wanted to be fast and easy. The obvious one was the guy who wants a stack to be crawled or not crawled. At the time that he's going to make a stack crawlable, he writes his program counter in thread local storage, and he writes a stack pointer after that in a coherent store order force. And the stack pointer in thread local storage was 0 if you were locked by the current running thread. So he's running, so that's why he's going to do it. So he just stores a non-zero stack pointer down. He's released his lock. On the clock cycle, he stores it down. He cannot touch it again until he can atomically swap a 0 in over that stack pointer. Meanwhile, the garbage collector says, I want. So he swaps in a locked version of the stack pointer, which typically just means he sets a low order bit and cases it in. And so the guy who wants to unlock it and run again does his cone stack pointer, which fails because the low order bit's not set, so he can't take that lock. That's how the lock works. So the lock has 3 stages. Stack pointer, it's unlocked. Stack pointer with a 1, it's locked by garbage collector, and 0, it's locked by the running thread.
So
unlocked, no one's touching it. It's locked by running thread, locked by garbage collector. 3 stages.
But you are talking about some kind of reusing the last bit for some type pointer tagging.
You're doing a lock. Every time you're doing a lock, all you can do is a word in memory, one exact word, which everyone agrees has the following meanings, right? And it's going to be, I own it, you own it, no one owns it kind of thing. If there are 17 people owning it, then you have to have 17 variations of who owns it or something that says no one owns it.
Okay.
Every lock on the planet, runs down this path.
Yeah.
Okay. Sometimes they have 0 or 1, locked and unlocked, but the guy who has it locked doesn't tell you who has it locked. So since you're only doing a word instead of a bit, you can say who has it locked at the same time as you say it's locked at all. This is what we were doing. Well, we were doing stack pointer because that was the key bit that won it. So the guy who's running fast and furious and not blocking for GC and wants just to run, to unlock his stack, he stores a stack pointer, he stores stores a program counter, stores a stack pointer, he enters native code, does his shit, gets out, he lifts up, he cases in his stack pointer to 0. If that was successful, which on a modern x86 is like an L2 cache hit, 12 clocks, predicts correctly, that's his overhead for getting in and out of his stack. It's a dozen clocks to do reclaim the stack lock, and a couple clock cycles to free the stack pointer, plus whatever other things you have to do to make a native call. So that was the fast path for a running thread doing a native call that didn't have to stop.
I'm wondering, we have in the concurrent collection space, we have like a lot of magic and intelligence going on in the garbage collector to determine, okay, we can collect this space of memory and we don't need to stop that thread over there. And I'm really wondering whether it's like we have like a lot of magic and intelligence in the garbage collector to reverse engineer this information. And I'm wondering what could be done from the language perspective to make restrictions on threads or tasks or pieces of code in general to say, okay, this part or this computation is isolated and it doesn't access the heap except for this place over there. And I think Erlang has some stuff, or I think Dart had something with isolates, but I'm always wondering because the requirements behind it are not that clear to me.
I went a long ways down this path for thread local stacks and thread local garbage collectors. And the answer was I could get 60 to 70% of all allocations stack local only, stack local garbage collected, stack local allocation. And that was not good enough to beat the Azul collector. It was still more efficient to let the Azul collector catch you up in the background.
But this sorry.
He didn't have any space issues like what you're talking about. He instead ran full GC cycles entirely concurrently behind your back all the time, and he was quite efficient at it. He requires a different mentality in how you code up the garbage collector and the interface to the runtime. There's a snapshot at the beginning and a snapshot at the end versions of garbage collectors. And the standard one that people normally use, snapshot, I want to say at the end, doesn't need a read barrier, and the other one needs a read barrier. And as soon as you admit a read barrier, everything else becomes vastly easier. So the Azul collector demands a read barrier. That adds some interesting measurable overhead on an x86. I think Azul beat it down to under 5%, but it's not 0. Whereas a standard card mark will be much, much less than 5% overhead for a generational behind collector. But on the other hand, once you play the read barrier overhead, the rest of the collector becomes a hell of a lot easier and can be entirely concurrent with everything else that's running around. And you get these super efficient, super low pause time, super efficient collectors. And you don't care about having special spaces that you know are safe or not safe, or I can collect this zone separate from this zone. Like Cameron's got zones that he's broken out by threads because that's how his model works. That makes a lot of sense. Having said that, I did my thread local thing. It makes a lot of sense. It sounded really good. In practice, the Zol collector womped up. It just ate everything up. So Cameron's solution may yet be more efficiently implemented by a bulk Azul style collector or not, I don't know. But it's not a foregone conclusion that it's a clear win to have a service-centered local collector, at least for implementation. For conceptualness, it's totally a win. Hey, this is independent from that. I want to know that I can collect this separate from that. That's great. The load on this is independent from the load on that. Turns out that the bulk efficiencies from having, the rest of the processor spare cycles, actually cleaning up GC across everybody, worked out great in practice. If you don't have an Azul collector and you don't want to do the runtime overheads, or you want to do the implementation details, make it work under the hood, having a stop the world in a service would be like I did stop the world on a per thread basis. It was pretty good. There's no doubt about it. It was conceptually kind of easy to understand. It was pretty good. This thread stopped, collected his own stack, and then carried on. He paid his own price. You had a pay-as-you-go mentality. Threads who allocated a lot, garbage collected a lot. Other threads did not and did not pay.
So how did the code make the
Internet cut out again.
Or 60 or 70, sorry.
Yeah, go back 10 seconds.
All right. So you mentioned earlier that 60 or 70% of the threads were determined to be
allocations on any, of the whole program's allocations would be done by a thread would himself do stack local allocations, but a bunch of running threads each independently had some ratios like that.
All right. Okay. So 60 or 70% of the allocations from each thread could be thread local, and the rest of them were global.
That's what we ended up with. This is a
right.
JBoss server under fairly heavy load.
I think that's the thing I'm wondering. Like, if we had language support for this to make sure at compile time to say, okay, this code only compiles if I can guarantee that it does not do any global heap manipulation.
Right. Why not do Rust style and be done?
That's probably going to be close, conceptually close in that regard then.
Right. So I would claim that the interesting price points here are the Azul collector, and it just cleans up well behind your back and you don't care, or your Rust and there is no allocation once he's got done with all his borrow games going on, right? And in which case that can be turned into some really efficient code. In particular, it keeps a whole lot of locality references the right way. Like any garbage collector that's doing bump pointer has locality references issues. I attempted to do the stack thing where I was hopefully getting better stack locality, and it wasn't quite good enough to pay off versus the shenanigans.
He will come back.
Ah, shit, everyone froze again. There
yeah, Cliff.
Just rewind 15 seconds.
Hey, Lisa.
No,
she's not here. I must say she's streaming, but she's not.
Yeah.
Go find out. Well, there you go. We had internet issues this morning too. And I'm wondering if it's like windy day. I wonder if like my cable is swinging in the breeze down the telephone lines down the mountain.
It's at what cable does your internet, or the coaxial cable?
Yeah, coax cable on the internet. Yeah, I'm sure it's running down the telephone wire and the power
lines. It loads 110 megabits per second, I believe.
Well, I mean, Comcast and speed tests will tell me I got a pretty good number. And
okay,
mileage may varies in practice.
To the thread allocation.
All right, what are we doing here?
Now it was starting to become interesting now.
Yeah. The takeaway there was either do a decent GC and then you can gradually improve it. And if you're going to do the Azul collector, pretty soon after you get anything going as a GC working well, switch to the Azul one because it needs the read barrier. But then it's conceptually, it's pretty simple after that. Or do a Rust thing, and then you're not doing any allocation on the, you're not doing nearly as much heap allocation. You don't care about GC, and all of your performance code does things that are going to be hot in your low-level caches. You're going to recycle the memory very rapidly because the program has annotated it so that you can.
The point of the GC is to hide all allocation from you.
Yeah, right.
So the GC, go ahead.
The GC is there to make life easy, so you don't have to think. And you want to do the Rust style annotations to make life fast when you care to think and you're worried about performance.
Thinking about it, I guess the balance of like ease of use versus performance is even shifting in a different way with value types, where we have like the garbage collected systems, but they might get faster due to not needing garbage collecting that much. It'll be interesting.
Wasn't the main point
not the issue
of the value type? Wasn't the main point to get rid of the object to drop down to underlying type on long, for example?
The issue. So pardon my French, but the fucking issue was people being fucking idiot. H2O does value types from 20 years ago and nothing to do with the garbage collector at all, and got giant performance wins for having value types. But I worked around the type system and I worked around the garbage collector. Okay, so I talk to people who do regular objects for ints and longs. I'm sorry, they do capital ints and capital longs, capital doubles, and of course Scala is sort of the famously bad example of this. And that's just like lazy on somebody's part. No, just use little l and little d double, and you get all the performance back. And the number of times where you have to do some screwball magic hack to get around the fact that you needed a big D for some library to pass a double in for a little d, that's like, you know, you're making excuses. Like deal with your code that, so you're using a double for a key. Okay, using double for a key. We'll make a version of non-blocking hash map long or doubles. It's like a cut and paste swap maneuver. Those things exist. It's nothing, I'm just saying non-block is mine, but other people have them too. These things are around. Primitive keys for hash tables. Why else do you need, what other things are you using non-primitive wrappers around items for? I claim you just want to go in your code and annotate it. I have a little d double and not a capital O object that happens to have a capital D double. And I have a billion of them. And so, you know, my life sucks because I have a billion capital D doubles. Don't have a billion capital D doubles. That's the answer.
Yeah, but isn't that like, couldn't you argue that like, don't do stupid stuff is like,
I know.
it's like the garbage collector is saving you from that. And now, like,
it doesn't save you from all stupid things. But
exactly, and now value types basically saves you from a bit more. It's like
you still have to come in and say I'm a value type, which as far as I'm concerned, you should have said I'm a little d double. But fine. This is like a, you know, it's array of structs versus struct of arrays. Like if you're already going to go there, just, oh, everyone froze again. Shit. Wow, at least this is bad. Oh, the internet sucks. Gee, mini Christmas. It's just a complete drop here. Oh my God. Shh.
A glyph. Oh, a glyph, you have to rewind by 30 seconds. Sorry. And you're muted.
Why is that? No one knows.
So the last thing I said before you went away was that basically garbage collection is there to save people doing stupid stuff. And I was wondering, like, adding value types on top of that is basically saving people from more stupid stuff, which if you argue that garbage collection is good for a use case, then the value types saving people more from stupid stuff should also be good. And then you went away.
Yeah, and all I was doing is ranting, which is basically you had to say I'm a value type. If you're going to say I'm a value type, why don't you just say I'm a little d double, not a big d double, and move on.
Scala doesn't have this luxury. It doesn't have a primitive types.
Yeah, well, that Scala needs to fix their problem, and they tried to with the specialization stuff, but they didn't get it
Scala,
right.
No, it just handed to the JIT to figure out what has to be from capital D2.
The JIT has its limits. One of them is escape analysis does not work well in large scales. So that stack allocation thing I was talking about with the Zool, that was done with escape detection, not escape analysis, which, like I said, doesn't work well in large scales.
I think in general, the problem is that if you're coming from the language compiler space, then it's really hard to thread through Java bytecode, Java assumptions, hotspot or other JITs and gets to the place where you want to be, because usually if you have some different language than Java, you want to have like a language that is better, which means it has a slightly to vastly different type system, and then you need to renegotiate between the type system you expose to your users compared to the type system you expose to the JVM, or you basically have to play by the rules of the JVM.
But so I would argue this is the Martin Odersky genius, because if you look at Scala, it's just on top of the Java type system, and it can lower it back basically through an erasure. That is the amazing stuff with the Scala type system.
Yeah, he did a good job with that one.
It's good, a perfect job, Martin. Perfect.
I think it's like we had back in the days, we had like words for the different failure modes. So we had like specification, where the specification simply didn't line up with either the compiler or the runtime, and then we had compiler fiction, where the idea of the compiler didn't line up with the runtime. And yeah, and if you have a look at all the, for instance, or at the access levels that Scala has that Java doesn't have, then it's basically just in the on the accessibility level, it's basically make everything public underneath, and on the type system level, if it goes bad, make everything object underneath. And it's even, if you had a look at Scala arrays, you had like, for instance, an array of int, an array of string, looking at it from the Scala point of view, with knowing that arrays are covariant underneath, you would say, okay, you can basically say, okay, both of these are arrays of objects. But then if you have a real look at a Java type system underneath, you realize, okay, there is no common ancestor between an array of int, because it's like primitive, and an array of string. So the common subtype, super type, is actually a object, or not array of objects.
Yeah.
And it's bad. It's like it always needed more runtime help, which Java or the JVM or the hotspot team, blame who you want, never delivered on. And part of that,
not never delivered on is not is too unkind. It would be sort of impossibly difficult to deliver this set of things you're saying without sort of a total rewrite of 100,000 man years of work, some ludicrous amount of effort.
But their main concern is Java. Scala is just
JVM was really for the JVM and running Java. We were happy to run other things, but we were not happy to add new semantics that were basic semantics that you're saying there. Rooting primitive int and capital S string in this common ancestor was not going to happen without a complete rethink and rewrite.
Yeah, sure. I think in that case, it wouldn't have been a smart idea, but I think there are other cases where I think more communication at both sides would have helped. So for instance, like if default methods in interfaces, for instance, that's a bit tragic that Scala really couldn't make good use of that. And there are always little bits and pieces where the slight difference between the ideas Scala had and the ideas that JVM supported snowballed in really, really terrible problems later on.
Well, what you going to do about
more
it?
Specific, but I would again say the Scala type system is the most advanced type system I have seen on the JVM, for example. It has so much types. It has types that even you cannot express in the source language, in this type, the rect type, the calling type, the recursive type, the type bounds, that some.
I'm just saying, the JVM is what it is. There are some things that it could have been flexible about. There are things that could have happened, and there are things that were probably never going to happen. Merging primitive int and capital S string in the same type hierarchy, not going to happen. Having tail call elimination in the JIT could have happened, could still happen. So they're saying there's some set of things that are reasonable to do without rewriting the world, and set of things that are not.
Yeah. Yeah, I think the point Tiro is making, I'm not saying that Scala doesn't have an advanced type system, but the parts where Scala has to interface with the runtime is it's like you can basically decide, okay, we want to have the best type system. We don't care about interop with Java at all, and then you don't need to worry about it, but then you also get really, really terrible performance, and all
I
the specialization Scala does is basically acknowledging, okay, we want to have some kind of Java interop, and we also want to have performance, and that's where all the pain starts.
I think the Scala type system was a tower above the Java, and you stack your types on top of top, and then erasure collapses back everything you do with the
and then you want the JIT to figure out who did what.
Yeah, you want to preserve useful information for the runtime to use, and in the Java bytecode case,
what I'm hearing is
there is no type information.
That the JVM team, Oracle and Sun, didn't bow down to Scala's requests.
No,
or JRubies or Pythons or Rubies or 15, 17 other new languages that came along afterwards.
No, I mean it's a runtime written for Java, and they care about Java.
Why should they comply with other programming languages?
That's my point. It was in fact a runtime written for Java, and that's
I'm not complaining. I'm just envisioning a world where people spoke more with each other, and could have been.
Java predated all these other languages by a long time. There was no one to talk to about it. When Java was coming around, your options were like C and Python, maybe. Python was hot and new, right? There wasn't no Scala, Groovy, JRuby, blah blah blah. None of that was around. So there weren't any.
Sure. I think it's not. I'm not criticizing the initial design, but if you look at these alternative languages, they are not that much younger than Java. So I basically think, like, from the point of Java 1.4 or 1.5, it would have been interesting if there was more.
Okay, so I can tell you why it didn't happen, why it wasn't going to happen. It wasn't going to happen, and I can tell you why. Because Sun was going to run out of money, and they knew they were financially not great. And from financially not great around 1.4, 1.5 to the following releases, it went downhill pretty fast. And at that point, it was, do we pay engineers to work on the current thing at all or not? It wasn't like we're expanding it because it ain't paying our bills. So it's all fun and games to say we had infinite money and we would infinitely solve this problem. The answer was we didn't have infinite money, and pretty soon there were going to be anyone working on the thing. So why the hell are we trying something new here or whatever? It wasn't going to make a difference.
Yeah. I'm not trying to change history. I'm just
So it didn't happen the way you wanted it.
Yeah, I'm speculating. Okay, I see we have like at the handoff point between the language and the runtime, we have these pain points, and how could the future look different if we had made small adjustments in the past?
Well, so from my opinion, the real answer is, what can we do now about it, as opposed to go back in time and magically pretend we did something different, right? Okay, fine.
I mean that's the point. It's like if you can only make that, you can only tell people to do things in the future if you learn from the past. And
okay.
So
I think there were a lot of lessons learned there. I think there's no one denying, like, should another reason for another JVM like thing come around. I think Microsoft tried, right? And they kept up really strong backwards compatibility. And I don't know why they didn't do the other things you needed to do. They tried a bunch of languages on it, but they never got the performance up. And everyone I ever talked to says, it's both performance and there's a bunch of other issues with their .NET runtime that weren't ever good. And I don't know why they didn't get those sorted out.
I mean, Microsoft is really strong in the language department.
Yeah.
And rather weak in the runtime department. And in Java, it's the other way around. And you can't be good at everything. It's just, you have to make priorities, otherwise everything is bad.
I'll say Microsoft could be better at runtimes, and Oracle could be better at languages. So I think we could both be better in either direction.
But there's a big asterisk on that, Simon, which is Java didn't have Java to look at. So when Microsoft came out with C#, it was largely copied from Java. In fact, it was originally being built as a clean room Java. And basically, the combination of lawsuits and other things allowed the engineers who didn't want to copy Java to go off in different directions every time they were dealing with lawsuits. So it became half Java, half not Java. But Oracle Sun before that had plenty of language brilliance. I mean, you're not going to find anyone in the universe with more language experience than Guy Steele, who's still alive anyway. And he's still working on Java today. Like, and they've got Sun Labs working on. I mean, they've got great depth. But they also are committed to backwards compatibility, which basically has hobbled them significantly on some of the things they'd like to do or wish they could do.
Yeah,
Well, Scala chose the JVM for a reason, for its runtime. It can.
yeah. Isn't there a Scala on Mono?
There was an earlier stage and is abandoned pretty quickly on Scala on Mono.
Yeah, I think it failed to garner interest because I think that the general problem in Scala was and is that it was always inward looking. It was always, if you had a new platform, the people always said, okay, we have this new platform, so all our existing users can write code on new platforms, but they never said, okay, we are now running on whatever, .NET or JavaScript. We are now allowing JavaScript and .NET developers to use
that
Scala.
That was pretty much happened with the Scala for the Scala for the Android platform. That was pretty much it.
I'm sorry, did you say Scala for Android?
Yep.
Yeah.
Yep. There was
which also like collapsed miserably because like people in charge said, well, I have an iPhone, I don't care. So
iPhones.
So the big people just simply didn't understand that like opening up like a new platform not only benefits the existing users but also allows bringing in new users, and I really never understood that.
If Scala's leadership recognized that the multi-platform approach for the Scala JS, Scala Native for Android, and from the begin to harness the teams and the talent and to invest in them, would be a different story, because we the de facto multi-platform language you wish for.
Yeah, I mean, then Kotlin wouldn't be slaughtering them on a lot of different fronts today. And maybe like the whole Kotlin thing wouldn't happen, or the whole Google adopting Kotlin thing wouldn't happen. It's like it would be a completely branch of history. And too bad.
They just saw the opportunity. Yeah. So I would say I would perfectly say that Kotlin is a stripped down version of Scala. For the purer Java version than what Scala can do.
Well, you're not gonna find a lot of people that all agree on language stuff. That's one thing you can be certain of with engineers. I would say that Scala, like C++, is primarily hobbled by its own weight, by its own bulk, its own internal inconsistencies. Scala is its own worst enemy.
Yeah, it's kind of I'm always amazed when Scala 3 was introduced as the simplified language, and they had like a dozen more keywords, and they now have basically you can do curly braces, you can do colon indentation, you can do colon indentation and with an end at the end, and you can do a colon indentation end, and then you can do end identifier. So you have like 4 or 5 different ways to write Scala now, and like the different ways are not interchangeable. So there are things that you can write with one style of braces, but not with other one, and it's
So Bjorn had the same problem in the 90s. He wanted people to use C++, and so he figured that if he took every feature from every language, that people would like C++ because it would have everything that they were looking for. And it turns out that that's not a way to design things. It's
If you
just
try,
not.
yeah, if
You
you
could
try,
argue C++ became still fairly popular, remains so today.
Well, no, I would argue that C being compiled in an IDE that claimed to be a C++ IDE became very popular.
See,
But it already
some
was.
extra extensions, but not all of them all at once.
Right. I mean, there are a dramatic number of products that are built in C with a few C++ features.
Hotspot being one of them.
Yeah.
C with
Hotspot
classes.
being one of them.
Rust
Yeah,
rewrite when.
single inheritance
C,
classes and very minimal
Dan's,
templates.
Dan's right. It's more like C with an occasional class.
I think I think it's interesting to see how the language decisions shape communities. So if you go like the C++ or the Scala route, it's like if you add features, you're naturally going to attract more users that like having more features. And as the community shifts, you with every feature you add to a language, the relation of the users that like more features grows compared to the percentage of users that want to keep the language small. And it's a bit like if you start adding features, you will never ever stop again. And that's yeah, I think that's an interesting language problem from a social perspective that we haven't really figured out yet.
Not only the social, there is always contention between extensibility and stability, because you always want to introduce new thing to the language, the cool stuff, the cool kid on the block.
Yeah, do you? I think
You
it's
you want to also have a simple core to get new users on board, or you age out the old ones and you don't pick up any new ones.
Yeah. Yeah, and in the end, it's like keeping everything stable forever is basically saying the existing users are more important than new users, which is certainly valid if you're like C or Java, but for many small languages with 1,000 users, maybe it might make more sense to focus on new users over your existing ones.
Simon, I was going to add on the GC topic. I have to run in a minute, so I'm going to stick this in and run. The studies we did at Oracle, and I actually saw one recently came out. I don't know if it was done by Oracle or someone else, but different GC approaches work well for different types of apps, or particularly different sized apps. And so the serial collector, for example, so there are, Artur, you can probably help me with this, but there's something like 25 different supported combinations of GC things, including like 6 supported base algorithms, right? So you've got serial, parallel, CMS, G1,
ZGZ.
G0, ZG, yeah, like, okay, so,
Yeah.
but the fastest GC is actually the serial collector. The second fastest GC is the parallel collector.
Oh, depending on how you define fastest.
Yes.
Exactly. So what I was going to suggest is that, you know, if you've got Mr. Hotspot on the call, think of GC to some extent as hotspot, right? Like your GC should be smart enough to adapt itself to the amount of memory and the types of allocations you're seeing.
GC ergonomics.
It's almost like as long as your heap is small, stick with a single threaded serial GC. It's your fastest choice. And at some point, go to parallel. And at some, you know what I'm saying? I've never seen it done, but if it could be done.
Okay, so you have, and you just don't know it. So the parallel collector will just run one thread if he's not got enough work to bother spawning another thread, and he'll be serial.
Okay, I didn't know that.
Yeah, he's got a heap size and count of cores. Certainly, the Azul collector throttles the amount of cores he's running for background to manage to keep up with the rate of what he's seeing and how long it takes him to do it. So a lot of the collectors do have these ergonomics built in where they pay attention to heuristics of how fast young gen fills and how fast Eden and old gen and yada yada, and they're trying hard to adjust. And then, you know, there was a long history of them not doing that or not doing it well. So there's a long history of people putting a bajillion flags. So all the flags are out there. They're all exposed. They're all critical performance for a bunch of old production VMs that no one wants to touch. You have to support all these bajillion flags, followed promptly by there's better and better and better heuristics that mostly work most of the time, except when they don't. And then you have to go back to the flags when they don't. And then there's a lot of people who learn one way or the other and they wouldn't touch the other direction. Like, I want to have my fine tuning on the damn GC because he fucks up so badly versus the guys who are like, oh my God, there's a billion flags and you can't ever get them right. So don't bother, just turn on the default. If it's not fast enough, you need a bigger heap anyhow, kind of, you know, mindset floating around. And the Azul went from the, you know, scratch with a new collector. And our first thing was, we have to eat all these other flags. And 99% of them we're going to silently ignore, because we had to run, but they didn't mean anything in the new collector world. They had no significant. So max heap, min heap were about the only ones that we paid attention to, certainly for a long time. I think maybe some more now. Probably Arthur knows more than I do, actually.
So what is interesting that we have this issue that, for example, for small containers, it doesn't make sense to run a concurrent collector, and it's just more efficient to to stop the world because the pauses are not so long. And yeah, we have this mode, but still, because it's just a change to our concurrent collector to run at a safe point, it's still not as efficient as it could be if it was a stop the world collector from the very beginning. So there are trade-offs, yeah.
Yeah, it's throughput versus latency.
Yes.
Yeah, I think it's like, it feels like the world, at least on the JVM, is marching through to more and more to the side of latency, and I'm slightly concerned about it. I'm always wondering.
Well, the problem with throughput is that you get the big pauses, and some applications can eat the pause and some cannot.
So
well,
yeah,
sorry. It is important for large applications like large heaps, but when things are running in small containers, they are small enough that they don't care, and that's an interesting transition.
Okay, yeah, fine.
I guess the consideration is that if you don't have enough throughput, buy bigger machines. But if the latency is not low enough, then you're screwed. I guess that's like if you focus on latency, it fixes like the issue that cannot readily be solved by buying bigger iron.
The deal with bigger iron is it immediately goes concurrent because the extra cores are not the same as a faster core. So suddenly you're parallel and concurrent. And if you have more cores, they can now do a background thing at modest overheads to your foreground, which may actually, I hear a lot of people saying, yeah, you know, concurrent versus latency throughput, but your burning cores make your GC take background, your foreground threads doing work actually are still running, and that still might be faster to get the job done than having a stop the world collector that periodically takes the big inhale pause because you did a lot of the work already in the background.
That's a good point.
Yeah, I think Camera's idea was that because there are these trade-offs and there are different implementations which do better in some cases and worse in other cases, why don't we do like a dynamic switching between them? And I think there is just an implementation complexity of it. Different collectors need different like data structures, etc. You cannot just simply switch it on the fly.
Big switch. Like your JITted code might be different.
Yeah.
You wipe
So
all
what-
your jitted code out, wipe out your entire heap structures, do a, serialize and deserialize from one heap form to the other, and then start jitting again. I think that's a big hit. I'm not sure.
Yeah, and what we have in practice, yeah, we have these either heuristics, but they are limited by a particular implementation. Like, as I said, yeah, we have a stop the world mode, but it's just a tweak on our concurrent collector. So it has this overhead, even in the stop the world mode, just because of the initial design of it.
Yeah. And typically your other performance issues dominate at some point anyhow, and you're better off spending that many engineering cycles on something else.
Well, and I guess the applications don't suddenly change their behavior like on the fly. You won't have a small application with small data set suddenly go to like terabytes data set. That is why I think having the flags set up initially is probably an okay approach to this. And the complexity of dynamic switching is not justified.
But if you have too many flags,
it's true.
If you have too many flags, what to do now?
No, I'm with the fewer flags are better.
Yep.
But then you have to make a call with, how much are you willing to hand out to the end user how your app works, which immediately goes to how much am I willing to nail down how my GC works. I cannot make any future improvements or these flags change their meaning. So the usual problem with flags isn't they're useless and you can ignore them. That's easy. It's they subtly change their meaning because the actual behavior under the hood has changed slightly. And so you have to go retune the flags from scratch, not just ignore them. Right.
Yeah, the flags become a part of your public interface, and you cannot simply drop them.
Yeah.
We've talked about this. Too many flags, and you're back in the programming land again.
Yep.
Yeah. I guess the flags are always static. You can only provide them once at the start, and the self-tuning runtimes. Sorry?
Varies by flag.
Okay.
Like you're not going to switch between ZGC and the parallel collector without a complete stop and rewrite the world. Everything's different.
Yeah, but where could you change things?
Max heap.
Okay.
How about a program some portion of a program running on the one GC, other program of the portion running on the other GC?
No, so as soon as you have two GCs involved, that you have a whole nother giant pile of engineering because they fight over basic
they
semantics.
Would be in a different memory regions, for example.
Yeah, right. Like I'm saying, they're gonna because a thread it kind of thread cross from one memory region to another. Yeah, I know you're looking to cause trouble. I can see the laugh, but that's what it is, right?
Yeah, of course.
So as soon as you're in different processes, you have already got that sorted out. But if you're in the same process, then I have to now do what a normal different process does. I have to have a way to enumerate threads that are running in this guy and threads that are running in that guy because they have different stack crawl semantics and different stack crawl behaviors, different thread locking and thread going, whatever semantics. And then secondhand call between them, you got more issues yet.
I heard that they have something like that in Chrome because they have basically several virtual machines. Like there's JavaScript engine, there's some rendering stuff that they have several separate heaps and they have different collectors working on them. And they somehow need to organize the interaction between these pieces.
Okay, I thought they switched to different processes pretty frequently.
I don't know much details. It's just secondhand knowledge.
Okay, fine. Yeah, like process per tab kind of things, which would immediately let you have a different garbage collector on every tab.
But even in one tab, you have this CSS engine, you have JavaScript engine, you have rendering of HTML. So
yeah, if you can agree on a common semantic for stack crawls and the like, then you can look at a pointer and do address space differentiation, decide which collector is taking care of it. There are obvious things there where there's a collector that says something about DOM refresh rates that wants to fire off 60 times a second and only at frame boundaries. And that's unrelated from the JavaScript that's executing, kind of unrelated. There's a thing there. We need to get a JavaScript implementation person on the call for that one.
Okay. JC, are we done with JC?
Well,
Yeah,
we
also-
That was the slogan, JC guilty unless proven wrong.
we could, you know, be done with a shorter meeting today. That's fine too. I don't care. Feel like
Will
I talked
be-
too much and didn't learn enough, so I should shut up more.
I think Cliff is dropping out. a
Oh, I'm
bit.
dropping again.
I'm not sure. Yeah, I was just saying maybe that the whole GC interop problem will get more interesting with JavaScript and WebAssembly. So from what I see is that they are working on some kind of interop system where they can mark references or pointers or whatever from the WebAssembly side to let the real collector, which is the JavaScript collector, know about these things. But I mean, it's WebAssembly. It could easily go in different. People could like write their own garbage collectors on the WebAssembly side.
Well, that was the proposal. My Twitter feed, somebody came up and said, "Hey, here's a WebAssembly proposal that lets us do garbage collection within WebAssembly, independent from everybody else."
Yeah, and then it will be interesting to see how the things interact. As usual with JavaScript, probably not too well, but
yeah, that's what I'm thinking.
if you, I mean, if you have billions of dollars or euros to throw at problems, even JavaScript becomes fast. So it's just another engineering problem, I guess.
Yeah, just another engineering problem. That one's it's like many of these problems that once the cat's out of the bag, you can't go back. And so
yeah, I guess that's especially true for the web technologies where it's really hard to fix anything once it's been used in the wild.
Yep. That was certainly it's a crazy ass disaster to try to engineer solutions around whatever. I tried, I had some good stuff come out of it, but man, I could imagine a simpler, more robust system pretty fucking easily.
Yeah, this reminds me of there's like this one glorious GitHub issue where people filed an issue with the Promise standardization group a few years ago saying that, well, promises are not monadic. They don't follow the monad laws in this specific way. And it was rebuffed by the person leading Promise standardization quite harshly early on. And since it's basically a ticket which will never be found by people who don't care, but basically everybody who hits an issue to promises not being monadic, Googles it, finds this issue and just writes another comment under it, and it's a train wreck that's running for multiple years, and I'll search it.
The Scala
promise. Monadic.
Yeah, the title is.
So this is a JavaScript, or are you talking about GitHub?
Yeah, let me search it really fast. I think because there's like the. Oh God! So the title is promises incorporate monads and category theory, which resulted very early in the reaction that was expected.
Throw it in the chat or in the doc.
So this is I throw it in the chat, and there is like one comment because it's like it spells out everything you need to know. Basically says, I love every additional comment here so many years later. I never muted this thread. The best part is that I have a lifetime of it to look forward to for two reasons. One, the things done wrong. One, the things done wrong here. are fundamental to programming computation itself. So there will never be a time when it's not wrong, and probably never be a time when it doesn't adversely affect programming in JavaScript. Second, those who think the conclusions here are okay will never search it up. This thread is kept alive by those who encountered the wrongness and searched the rep for what went wrong. So for those arriving now and never, welcome, you are in a good company. And it's like the whole thread is amazing. So I think the basic problem is that the then methods in promises in JavaScript unwraps. So you can put a promise or a normal value into a then, and depending on what you do, the value is either unwrapped when it's a promise, and it's not unwrapped when it's not a promise, and that's conflating the map and the flat map method using Scala speak here. And I always forget the Haskell names.
Haskell is bind and
bind an fmap or something.
Yeah.
Yeah. So and that's bad for various reasons, and yeah, it's like one of those JavaScript things that once done, you never can fix again.
Okay.
I'm busy reading. There's clearly some opinionated people here piling in.
Yeah,
I'll quit now. I'll read it later.
It's like if you scroll up and then see 218 hidden comments, then it's
yeah.
Well, everybody has an opinion. Why not?
Yeah,
we
true.
all have it. We all have our opinions about what the thing should look like.
Jeez.
Yeah, but sometimes it's just math, and math usually wins over opinions.
Yeah, the math aspect, I agree. So, okay, anybody have some?
No, okay, fine. I've quit reading now. Yes, there are people ranting on each other. Oh, excellent. Fine.
Next topic. Do we have
value types? We mentioned value types.
Okay. Yep.
During garbage collection discussion. I don't remember. I wasn't paying that much attention, honestly. Like in my language, the way I don't have garbage collection, what I have is I'm trying. There's this paper called "As Static as Possible Memory Management," and what it basically does, I mean, this is my interpretation of the paper.
throw a link in later?
It builds a state graph of the program, and then it says for each state transition, did I lose? Am I moving from a state where I can access the memory to a state where I cannot access the memory? And if it does, then it inserts a free statement along that state transition.
And
so,
how do you dynamically track, reference counting, et cetera? How do you dynamically track that you're losing the access?
So it's a static analysis. It's like, I mean, there are these algorithms that build a state graph of your program and say, okay, it could be in, it can move from like being in this function to being in that function. And the stack will look like this, and the heap will look like this, and so on. And so, I mean, I won't say they're perfect algorithms. I mean, I've been reading, and they basically say they crash if you use anything, because they get into an exponential number of states.
Well, right. That's what I'm saying. You can't. It's not exponential. It should be infinite. And so the question isn't.
No. It's exponential because the infinities are very easy to represent as unique symbols. It's exponential states where you can be in state A and not in state B, and in state C and not in state D, and so on. And so that's
okay, fine. So right. So now that you're exponential, what are you doing about it? This sounds like not worth it yet. I mean, or not solvable.
I'm writing. I could just say, oh, you shouldn't write complicated programs. Write simple programs that work. And like, if anybody actually wants to use my language, I'm sure there's some way to make to hack the analysis to like make their program work.
It will emit a big message. It will say, I like the program right this way and not this way because I'm the compiler.
Well, if you can write the message, but instead you're gonna have to say is, I don't know how to do this one. So, you know, performance will suck. Do you want to go there?
Well, so no, I mean, the thing is he proved in the paper, he proved that it covers reference counting and the linear type systems like what Rust are using. So like if you use either of those styles of memory management in your program, the analysis will work. It'll converge. So it's only like really complicated programs where it won't converge.
Hand over hand.
What?
Style, hand over hand locking, hand over hand memory management, double buffered, where you just constantly have one new thing and one old thing, and you're moving shit from the old to the new, and you want to recycle the old one, come back round. You do it explicitly with double buffering, but implicitly would be, you know, you know, in the case of a malloc and free system, when you freed the last old guy and you malloc the new guy, you would just pick it off the free list, and that would get you the reuse you're looking for right away. So I'm just like sorting out, you know, what it would mean, or is there a way?
I feel like that would work with the reference counting aspect, because you would just say, I mean, you would just, I mean, like everything would have one reference, so it wouldn't.
So what was the value aspect of value types aspect?
Anyways, but yeah, no, that was just what I'm doing in my language, so I don't pay attention to garbage collection discussions. But no, for value types, I was thinking the interesting thing was like how languages like C and stuff, they have complex number value types, because their semantics for specifying compound data types do not allow you to specify a value type. You have to specify a reference type. So what they've done is they've gone in and they've hacked the compiler. So say, oh yes, this complex number is actually a value type, even though you can access its fields like a struct.
But how it's represented, the complex number?
Well, it's just two numbers. It's an X and a Y coordinate.
That allows you to specify it as somewhat atomic or somewhat primitive or somewhat.
Right. Are you saying that they do let you get at the address of independent fields? So the claim is it's actually really a reference type under the hood.
Let me look at this. I don't think they actually let you get the addresses of the fields. I think you can only use them as numbers.
So if you just don't have the address of the fields, that just says they have a group object or a bulk tuple collection, and you can talk about individual fields, .field syntax, but there's no memory involved yet. And the complex is being passed by value, and it's taking two registers probably, or maybe it's passed on the stack, but there's no memory. There's no unique memory ID for it. There's no reference.
Yeah. Let's see. Oh no, okay. So that's what it is. They're macros. So like you have an imaginary macro, and if you call C real of a complex number type, you'll get the first coordinate.
Yeah, because the complex type is it has two numbers, a real part and an imaginary part. There, I believe it's sufficient to be represented by two numbers.
Yeah, but the question is, did you have a reference? Is there memory allocation? I make 1 billion of them. Do I burn 1 billion pieces of memory? Do I have to free it later? Do I have to free 1 billion things? How is the memory tracked?
And it's handled like a number type. So if you store it in the stack, it'll be in the stack. And
okay, so that's just yeah.
To a value, and that'll be on the.
So that's just another. I want to say a scalar. It's just a collection of bits that they're passing by value around.
And
the value type, yeah.
Being a struct, which is well.
I'm sorry, I didn't understand the question. Then it's clearly a value type. You can get at the individual fields, fine, but it's a value type.
Right. Well,
It's not, I would say it's not really much of a compiler hack.
Hmm.
As soon as I have any of the bit fields are essentially value types.
Yeah, well, I mean, the question is why you have to declare a separate complex number type, and why you can't just declare a struct complex number to be two double values.
Oh, that's what I'm working on in AA. So that one I claim you can do, and I'm doing, but that's not C++. I don't know, but I'll throw out this one. Those guys in the C++, they have some backwards compatibility issues, and they have a whole lot of people who thought for much longer than most languages get thought about how to do these things. So it's likely the case there's some backwards compatibility fail that's not obvious.
I think there is an interesting article series on people trying to fix or improve things, and it being really, really hard for completely unexpected reasons. I'll have a look that I can find it.
Yeah. You hear shit like, we finally decided to drop support for the 37-bit CPU processor, the Burroughs 37-bit CPU processor from the 60s, right? And you're like, holy Jesus, with one's complement math and shit like that. And then we can now make the following, whatever, free up some constraint by, you were supporting what? Fine.
I think one of the article series is this one here from the PhD. And I know there is another one that's equally good. I'll have a look.
Oh, CABIs, yeah, they're pretty ugly.
Aren't they changing from version to version? Or it's just one, maybe?
I think the problem is they have these tuples, so it's not for version, but it's for a platform architecture plus an OS plus the compiler itself. And yeah, so even compilers on the same platform, on the same operating system, have not necessarily compatible calling conventions, for instance. I think the most well-known issue is with I think GCC and LLVM disagreeing on how to pass around things for SSE if some weird special cases is hit.
Yes. All right. So what are they complaining about CABI? I know what it is.
Yeah,
Yep.
I don't know. I didn't research it that much. I just thought it was interesting that there was a complex number type in C.
Yeah. Well, there's an ABI. And now, I mean, that was that conversation. And now how do you map your types to the ABI? And then you get an ABI baked into your machine code you've just generated because you're passing around wads of machine code as DLLs or SOs or whatever. And they only cross call with each other if they all agree on the ABI down to some pretty fine bits. And so pre-cooking code, like not jitting, but ahead of time compilation down to an ABI means that you also have a way to diagnose and agree on what the ABI is and how they talk to each other. And then if you don't have the right ABI, they can't talk and it doesn't connect, or it crashes silently when you load the DLL because some of the ABIs look good and sounded right and have all the right bits, and then they lied about how they did the layout. And I saw somebody else do a much better job of tearing apart the current x86 ABI issues between GNU and Microsoft, several other people. And there were some like tried hard to have underscore x64 or x32 and something other letters thrown in would tell you which of the ABIs they were talking about, except for backwards compatibility, they cheated on a couple of them in a couple of directions, and then, you know, there's a thing there that says something that they need to have a little more complications about telling by looking at a file name or looking at the file first few contents. I know what the ABI is, and I'll at least not let you try to call the incorrect one. I'll just tell you at link time or at load link, you got the wrong kind, and I'm done here.
That's I think this whole legacy mess makes me really uncomfortable with operating systems that mandates that system calls need to be only made through the Libc, which I think is like terrible. It's like in most cases, I think most languages except C or C++ would really benefit from just calling the kernel and getting the results back in the way they want, instead of telling Libc to call the kernel, and Libc does random magic underneath, and then you get something back which might make sense in C and involves this error number macro, and
right in the land of forward moving compatibility with kernel revs and libraries. If I get a new kernel rev and has some cool shit I want out of my kernel, do I have to recompile every piece of code I have on the planet because the ABIs changed for some of the calls, or do I link in a new libc that came with the kernel that shuffles the arguments the way that are necessary for the new kernel? So that's you know, we added a layer of indirection in order to allow us to mix and match your JITted code or your hard AOT compiled code with different revs of the kernel, which are using the libc to map the calling conventions around.
So I'd say that's the responsibility of the language runtime. So if you have a language runtime version that supports the new kernel,
you
then
fell into my trap.
Yeah.
Yeah, sure. So Oracle, please, Mr. Oracle, I'm Ubuntu Debian blah 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 version XYZ. I want to go to XYY. I'm going to flip the registers around so I can support having an infinite sized pointer off to more whatever I'm doing. I'm doing something a little differently, right? And all your existing library calls are now broken because I need to do a register shuffle. So please recompile everything you ever did for Debian. Make a new hotspot that's Debian Rev XXX specific. And Oracle will look at you funny, cross-eyed, and like, yeah, right, guy.
No, I think my main attraction to it is that the kernel ABI is more stable and more, I say, static to understand. Because if you look at the C ABI or the C API Libc gives you, it's like it's impossible to understand what it actually means without like resolving 20 macros and compiler built-ins and random stuff. I don't really care about.
That's like a different problem. I claim there makes sense to me to have some kind of wrapper layer that I would call for 99% of my OS calls, because all I'm doing is meeting the shuffle in the correct way for the kernel of the moment. And I don't care what the kernel wants under the hood. It's going to do what it's going to do. And then there's something the kernel did that's new and different. Like I went through the transition of there weren't sockets, there were sockets. And everything else with file IO was going on was unchanged, but sockets kept shuffling. Well, at some point they had file handles and socket handles, and they wanted to shuffle to make those compatible, do something sensible. And if you didn't have a libc interop layer, you had to recompile everybody in the planet. So libc showed up with I'll map your file handles and your socket handles, and I'll ask the kernel what rev is, and I'll flip which of the ways I do the layout according to what the kernel believes is the right way. So we could have a smoother transition. So not saying that it was good or bad or whatever, just saying if you demand a hard connection between this thing and that thing, they can't move independently.
Yeah, I'd say it's like it's the responsibility of the language runtime, and not the responsibility of some weird native library from a completely different other language that does things completely different.
Well, I would claim that a version of libc that's wrapping the OS calls is part of the kernel. It's part of the user-facing side of the kernel.
Yeah,
and I would love to believe that it didn't require some special compiler magic of some kind, something fairly straightforward. It has to have some compiler magic because ultimately it's making machine code to talk to machine code. So there's some forced layout going on that's not part of the C standard where I have to go lay out objects in this particular way.
Yeah.
You could have, you could argue Google protobuffs is what you want to have here, you know, something like that. But you want a soft transition between the layers, or else you have to have Oracle recompile a new hotspot for every minor rev of every OS on the planet, and that's not happening.
I'd really prefer to have a spec at a kernel API level or ABI level that says, okay, you use this system call number, it expects the following registers, and you get a result back in the following registers, deal with it. And not the C things with dozens of macros and things around it. So I mean, it's like a fairly large languages with fairly good compiler teams have given up on understanding these APIs. Say, for instance, Swift just embeds the C front end into the compiler so that they that I think embedding is the wrong way, but they just use the LLVM C stuff to basically understand what all the C code means, because the code is simply not a good description of what actually happens for every
different problem that I can get on board with, which is the description of the kernel calls is done in this very obtuse way from layers and layers of C with macros. There's another version, I'm going to use protobuffs as an example. I don't care if I'm the right thing, but something like protobuffs that come along and say, this is the layout, this is the registers, this is the, and that it's machine readable, and that there's a very straightforward JITting technology that could read a simplistic version of protobuffs and just cough up a mapping from whatever I want to have to whatever the current backend.
Yeah, I would love that. And it's some operating system.
Again. Wow. All right.
Welcome back.
Yeah. All right, let's wrap it up. I'm tired of fighting this fight. I'll go have a conversation with Comcast.
Okay, guys.
All right, have a nice day. Have a nice evening. Hope you have such great weather as I have. And see you next.
All right, next week, maybe my Comcast will be better.
Okay, next week. Bye.
Bye.